All right, let's talk about rotation about a fixed axis. Well, we know what kind of motion is that. We talked about this when we were talking about kinematics of rigid bodies. Now we want to know how can we actually take kinetics into account when we are dealing with this type of motion, right? We saw how could we study the acceleration, velocity, uh, of acceleration and velocity of rigid bodies when they were going through a rotational motion about a fixed axis. Now we want to know how can we relate this acceleration, the type of motion we in this type of motion we have to forces and couples, right? That's the whole idea of kinetics and the whole idea of dynamics, using both kinematics and kinetics to study the motion. Now, for translational motion, it was pretty straightforward. We used Newton's second law for center of gravity, and then there was an extra equation which we were using, and it was telling us that the moments created at any point on the rigid body, with all the forces applied to it, the summation of all the moments caused by those forces should be zero. Pretty straightforward since there was no rotation, and that was just the added equation. And we could use that along with Newton's second law and whatever we know from kinematics to solve the problems and find what we were asked for. Now, when it comes to rotation with a fixed axis, we are still going to use the Newton's second law, but we're going to use a different version of it. I would say the rotational version of Newton's second law. So we use Newton's second law for rotation. Let's say we have a rigid body. Remember, I typically, or that's the norm. They typically draw the rigid bodies like potato-shaped objects. So I'm just gonna draw something like this here. And let's say since we're dealing with the rotation of the fixed axis, let's say this is our fixed axis at point O. Right? And we have this rigid body rotating about this axis with some angular acceleration alpha. It's rotating about this point O, and the axis of rotation is passing through point O, coming out of the screen, or coming or going to the screen, depending on which direction you want to take your axis. The positive direction of your axis. Now, so what we do is, let me write it down. We use Newton's second law for rotation. Let's see what it is. We use Newton's second law for rotation. Let me define it, which can be defined as this. Now, what does this law say? There's nothing new there, but we are just replacing the forces with moments and the mass with mass moment of inertia. Remember, in the lecture we were talking about mass moment of inertia. I explicitly told you that mass moment of inertia is the rotational equivalent of mass, and that's where you see it. So it tells us that the sum of the moments some of the moments about a point again about a point due to external forces and couples equals the product of the moments of the moment of inertia of the rigid body about that point. Right? And the angular acceleration. That's it. So the sum of the moments about a point due to external force and couples that is equal to the product of the moment of inertia of the rigid body about that point and the angular acceleration about that point. So if I want to write it in mathematical term, summation of all the moments, in this case we're looking at point O, since rotation is happening about that point, is equal to mass moment of inertia about point O times angular acceleration. We know how to deal with angular acceleration from kinematics. We talked about mass moment of inertia when we were talking about, we talked about I when we were talking about mass moment of inertia. And here, what I'm telling you is that this product of these two is equal to the summation of all the moments about the point that we are studying, the rotation about it. So that's pretty much it. That's the only equation added to the bucket of all the equations and knowledge we had from before related to kinematics and dynamics. So we are going to use this. Well, we know how to calculate mass moment of inertia. We know how to calculate and deal with angular accelerations. Right? We saw it when we were talking about angular kinematics of rigid bodies. We saw it when we were talking about kinematics of particles. So this is not a new term. And next, I'm going to take a look at a couple of examples to see how can we actually use this expression, how can we use this relationship to study the dynamics of rigid bodies when they are rotating about a fixed axis. So this should be, I just noticed, this is the second type of motion. This is rotation about a fixed axis. Just want to fix that. The first one was translational. This is rotation about a fixed axis, and later on we're going to talk about the general planar motion. So let's take a look at those examples and see how things work.